Hello and welcome. In this video we're discussing a classic simulation challenge, efficiently simulating massive complex structures. Finite element analysis is essential, but solving these models can be computationally demanding. That's where substructuring comes in. Today we'll do a deep dive into component mode synthesis, specifically the top-down approach in Ansys Mechanical, demonstrating how it can possibly streamline your FEA workflows. Before we get into the details, let's first understand what substructuring actually is. It's all about efficiency. Handling a massive system with millions of degrees of freedom is impractical. Instead, we reduce it to a super element that retains its key properties, mass, stiffness, and dampening, while drastically cutting down the computational load. This technique is essential for analyzing massive structures like aircrafts and nuclear power stations, or any system with repeated components. Now that we know what substructuring is, let's talk about why it's so powerful. Here's how it helps. It reduces computational time, letting you solve gigantic problems without the need for a supercomputer. It helps reuse substructures, so if a part repeats, you only compute it once. It prevents recalculation in nonlinear models, saving time and iterative simulations. It also allows different team members to work on separate components, integrating them later in a system-level model. With this foundation, let's move into how substructuring works in Ansys. Substructuring in Ansys follows a structured workflow, specifically the component mode synthesis method, which has three main steps: a generation pass, a use pass, and an expansion pass. During the generation pass, the substructure is reduced to a superelement, creating a simplified mass, stiffness, and dampening matrix. During the use pass, the superelement is integrated into the full model for analysis. The expansion pass, which is optional by the way, restores full displacement and stress results within the superelement for post-processing. Understanding this workflow is key before diving into specific approaches. So how do we actually create a substructure? There are two main approaches here: top-down substructuring and bottom-up substructuring. Top-down substructuring extracts substructures from an existing model. The generation pass is run while ignoring the non-substructured components. Bottom-up substructuring creates substructures as independent models, which are later assembled into the full model. For this session, however, we will only be focusing on top-down substructuring. Now that we've chosen the top-down approach, let's see how Ansys automates much of the work. CMS in Ansys Mechanical happens within the condensed geometry object, where you can define condensed parts that hold all the relevant data. You can make use of automatic interface detection, which helps identify contacts, joints, and applied loads. And matrix reduction and interface methods are handled with minimal manual input. Now let's break down the key concept of condensed parts. Condensed parts are the backbone of substructuring. Here's why they're critical. They store all the necessary information for the generation pass. They also define master degrees of freedoms, usually at contacts, joints, and applied load points. Ansys also has the awesome ability to automatically detect interfaces, making the setup way easier. But before we use them, there are a few key considerations. When setting up condensed parts, keep these in mind. They can consist of multiple interconnected bodies. Nonlinearities shouldn't be included in condensed parts as they will be ignored. There are also multiple valid connections, which include shared topology, beam connections, distributed mass, point mass, spring connections, fixed joints, and bonded contacts. Now let's talk about defining interfaces, which are crucial for a smooth simulation. Interfaces determine the master degrees of freedom, which connect condensed parts to the rest of the model. Common interface types include geometry, name selections, loads and supports, point masses, connections, and remote points. Since interfaces directly impact solution time, selecting them properly is crucial for efficiency. After setting up condensed parts and interfaces, we can finally analyze the results. The expansion pass restores detailed results within the super element. By default, only interface displacements are available, but using the expansion settings, you can retrieve full stress and displacement results. Having now properly discussed what substructuring is, what a super element is, and what the CMS top-down method is for creating a substructure. Let's dive into a practical example of how we actually do that. So in this example, I now have Workbench open. This is Workbench 2025. First thing that we should always do is save our project or our Workbench so that we aren't working out of a temporary file. Our file is now saved. To get started, we will open Workbench. As you can see, I am going to head straight over to the harmonic response in the analysis systems list. I can either double click on harmonic response or I can click, drag and drop in the green space, which is the way I'm going to choose. For this particular example, we are going to be carrying out a harmonic response on a wing section, or the section of a wing. And we will simply go ahead and import that. It is already a drawn geometry, no need to process it. It has already been processed. We're going to dive straight into the model. I'm going to refresh the model, and then after refreshing, I will open the model. The model has refreshed. I can double click twice, or I can right click and click on edit to open Ansys Mechanical. And we will wait again while Ansys Mechanical opens. There we go. Ansys Mechanical has opened. We can now see our wing section, our geometry sitting in the middle of the graphics pane. And we can see that we have got just a small section of the wing. We have got the leading edge. We have got the main skins on either side, the bottom and the top. And then we have some webs in the middle with some spars running through the wing. In this case, for this particular example, we are going to make super elements of our spars running through the wings in order to reduce the complexity of the model as a whole. Just a quick disclaimer, all the values that I'm using in this demo are arbitrary. There's no particular reason for them or no particular science behind them. This is purely just to get the idea across. To get started, what we will do first is we will add a fixed support to our project tree. Now, one important thing to note is for every condensed part that we have, that condensed part requires its own boundary condition to be applied to it. We cannot go ahead and apply a fixed support to the whole one side of the aircraft wing geometry section that we have here to fix it in place. If we are going to separate these spars and make a condensed part out of each of these little spars, we need to have a fixed support for each spar. So let's do that. Okay, I'm going to first do a fixed support for these faces over here on the side of the main skin and leading edge skin. I should not select that. There we go. These I can put all together because these are not going to be condensed parts. However, these sections over here will be, these spars will be. Let me add a fixed support and a fixed support, and then lastly a fixed support. Great. Now on the other side, we are going to apply a force to the exact same faces, just on the opposite side of the section, and the force will just be applying an arbitrary number, which will be 500 newtons on each boundary condition here. So again, just going to do that, apply. I'm going to change it from vector to components. If you didn't know that you can double click to cycle through options in mechanical, now you do. Let's add another force here. There we go. I'm going to add it to this face here. Apply, cycle through, 500. We're just going to do that 2 more times really quickly on the other 2 spars. Go 500. And then insert this one as well. And 500. So now if I look at my harmonic response, So now if I look at my harmonic response branch, I should see that I have fixed supports on this side, I have a total of 4, and I have a total of 4 forces being applied on the opposite side. Now for harmonic response, we can have it as a pre-stressed harmonic response. We can also have it as a modal harmonic response, where we take values from a modal or from a pre-stressed static structural, and we bring those values in. In this case, we're going to be just running a harmonic, super standard, simple harmonic simulation. Now working from the top down, we are not too worried about geometry imports. Everything is sorted there. We are not going to be diving into material properties in this video, so everything is going to be left as is over there. Materials the same, coordinates we don't need to add anything there. Connections we might have to change later on, but we'll have a look at them in a little bit. What we do need to add to our model though is our condensed geometry. So if we click on that, you'll see it populates the outline tree with a condensed geometry branch. If I click on that, you'll see I have options at the top here to add a condensed part, an imported condensed part, or just get solution information. I'm going to go ahead and add a condensed part, and I'm actually going to go ahead and do it 3 times, as we have 3 separate spars which we would like to turn into condensed parts. Adding a geometry to the condensed part is super easy. I simply click on the condensed part. I can click in the geometry field. You'll see it tells me, or it asks me whether I'd like to apply or cancel. I can select my geometry. I just have the body select function on at the moment, and I can click apply, and it applies it to that geometry. It makes everything else transparent so that I know what I've selected, and I just need to go and repeat this now 2 other times for the other geometries. There we go. And that is the last one. Now from here, you'll see as I've been carrying on, all of the boundary conditions which I have applied to these spars have now got question marks next to them. This is just indicating that I need to update the geometry, the condensed geometry section before these will be fully defined again. And once we update this, all of this should fix itself again. Looking at the condensed geometry, we can select each part individually and play around with the settings if we would like. For now, I'm going to leave everything as is, as the default settings are more than sufficient for what we are doing today. Okay, great. Now that we have created our condensed parts and we have assigned geometry to them, we have to go and see if Ansys can identify all the interface points at which they interface with the other geometries in the system. And then from there, we can go ahead and create our actual super elements. How do we go about doing the automatic detection? Well, we simply click on a part. We can right click on it. We go all the way down the menu to the 3rd option, which says detect condensed part interface. We can click on that, and you'll see it's good to go. It has identified all the areas where it might come into contact with the other bodies, and it has also identified the areas where it may have boundary conditions which are applied. This we can all see in a more metricized view down in the table here below, where we can now see that we have contact regions. We also have a fixed support and a force which is applied. We can now do the other 2 quickly. I can multi-select them, I can right click on them at the same time, and I can say detect while both of them are selected so that they both run through the auto detection process simultaneously. And as you can see, they too also have contact regions and fixed supports and forces. So I think we're all good to go here. We're going to right click on condensed geometry, and we're going to say generate condensed parts. This will require the mesh. So once the mesh has run, the condensed geometry will then run, and it will create our super elements for us. Okay, now that our super elements have been created, we can go ahead and click on one of our condensed parts to have a look and see maybe there is some information that is useful to us. For example, over here we've got a number of interfaces and a number of master nodes. This number of interfaces should reflect what we are seeing in the table on the right hand side, 1, 2, 3, 4, 5, 6, 7, where the number of master nodes is the amount of nodes that are all connected to these interfaces that are listed on the right hand side. So that is essentially the amount of nodes as a result of the mesh. And we can go through each part and we can see what each part looks like. Essentially, this one has 8 interfaces and a slightly higher number of master nodes. And then lastly, we have another one with 7 interfaces and also quite a few master nodes. Once we've done this for harmonic response specifically, we need to go to analysis settings and we just need to set a range for the simulation to take place. And after this, we've got no issues, no errors, no question marks, which means we are all good to go and run our simulation. One thing that we can check maybe just before quickly is we can make sure that our displacement values are all turned on and our all results are also turned on. This will allow us to pull values such as displacement values and stress values in certain cases from our super elements once the simulation has run. So let's go ahead and solve. Our simulation has just finished running. So now we can go ahead and click on the solution branch so long, and we can already see some useful data. For example, we can see all the different frequencies at which different results were extracted. And if we want to see the plots, we can go ahead and right click, say insert deformation total, for example, right click insert if we want to have a look at our equivalent stress. And we can right click again and say evaluate all result. This you'll see brings up the green tick showing that things have been calculated, and over here we can see that we get full deformation plots as a result of our harmonic response. We can also have a look at our stress values. And we can always compare this to a full non-substructure model to see whether or not our values compare. Lastly, let's play around with our connections to see how much of a difference they make when it comes to affecting the condensed parts, and then in turn, how much of a difference that makes to the results. We are going to go ahead and expand the connections branch, and as you can see, we have quite a few contacts. I'm going to go ahead and select all of these, right click, and say rename based on definition, just so that I know exactly what I'm dealing with. As you can see, we have quite a few parts that connect to our spars. What we want to do now is we want to go ahead and interrogate each of these contacts to ensure that the interface is simplified as much as possible to ensure that our master nodes are as little as possible when looking at each of the condensed parts. This specific number over here, the number of master nodes. This number of master nodes may decrease as we interrogate our contacts further. This will be due to the fact that there may be an overscoping of faces between other geometries from the spars to other geometries as a result of the automatically generated contacts. And once we have fixed those scopings and we have reduced the number of faces that come in contact, we can expect the number of master nodes to decrease. So let's give that a go. I'm going to select the first spar over here, see where they're connecting. These rounds I'm going to remove for now, so we are going to have just this one face. I'm going to connect, click target and accept, and I'm going to go and quickly do this for each of the places where these spars come into contact with other geometries. I will see you in a few seconds. I have gone and updated all the contacts so that all the faces that should be contacting are now contacting, and any faces that shouldn't be contacting are no longer contacting. And with that said, we can go ahead and we can generate our condensed geometries yet again. Now that that is generated, we can select our condensed part, scroll down, and we can see that the number of master nodes has indeed dropped, indicating again that the master nodes are dependent on the interface between your condensed part and the other geometry in or geometries in the system. And that is how you carry out substructuring in Ansys using the component mode synthesis top-down method. Thank you for watching.